integrating cloud storage providers in genome space. I'm also from UCSD, well, from San Diego, that is, not from the exact same thing. I never sit beside the beach when I'm coding. I think I'm doing it wrong. So we've talked about genome space at BOSC before, so I'm not going to go into it in any detail here. Basically, the goal of genome space is to make computational analysis available to biologists with any level of computational background. So genome space basically functions as a lightweight integration layer that lets you pass data between tools easily and between different cloud storage providers easily as well. Analyses are not actually done by genome space, they're done within the tools themselves. And lastly, there really isn't just one genome space anymore. We're now up to 3 at the moment. There's the original genome space, the one that I work on. There's one called Genome Space Australia, which is part of the Genomics Virtual Lab run by the University of Melbourne. And the NASA Gene Lab project is now spinning up a 3rd one to be part of their backbone. So at the moment, there's about 20 tools in genome space. These include some data sources that give you things like expression data or genomic coordinate data like UCSC. And then there's a bunch of tools themselves, some of which are actually aggregators of tools like GE Workbench or Galaxy or Gene Pattern. So there's actually literally over 1,000 different sorts of analyses that you can use there. And what genome space is all about is making it easy for people using any of these tools to get their data, to get their files basically into and out of any of the different cloud storage providers that are there. So this includes, S3, Dropbox, Google Drive, and Swift right now. And yes, I am saying files. I know it's sort of old-fashioned, and you might also have noticed too that those cloud storage providers, none of them are actually file-based. So really what we're talking about here is just named collection of bytes that have some persistent identifier and have some accessibility over the net. When it's sitting quietly on a disk drive somewhere, it might actually be a file, but it really doesn't matter in any particular case. Oops. So the genome space architecture looks basically like this. We've got a couple of servers for managing user identities, for managing tools, and for managing data. But we don't really do much in the way of managing data itself. The way that we're integrating the cloud storage providers is that pretty much everything you do, anytime one of the tools requests a file, it goes to genome space, the user gets authenticated, and then we generate a one-time use URL out to the actual storage provider. So when you're trying to get a file from us that's on S3, you'll actually retrieve the file from S3, and the file actually lives on S3. Same goes for Google Drive and the rest of them. The advantage to this is it means that the actions are pretty lightweight and all of the downloads and uploads happen very quickly because you're not actually going through us causing a constriction to the pipe. So if you want to access the data or the files in a cloud provider that aren't there yet, is you would go in and make a new implementation of our file system interface. Yes, we're Java. We've got a bunch of these right now, including one that's just for local files on disk. The thing is, you usually don't have to do this. If you have a cloud storage provider or something of the sort that you think would be useful, it's probably useful to others as well. So the Genome Space core team would be happy to go out and make a new implementation for you and put it up, because then all of our collaborators benefit from it. But you don't have to do that. If you want to, we are open source. It's all LGPL, and it's sitting on Bitbucket. So you can go in, pull the code, start, make the new one yourself, and put it up there and give us a pull request. So this is how we actually got the OpenStack Swift connection. That was done by the guys at University of Melbourne. They just gave us a pull request, and the merge is pretty much almost complete. That's going up on our production server in the next couple of weeks. So if you're not actually writing the Java, then you need to talk to get the file somehow, talk to us to get the file somehow. We have a RESTful API. Now, trying to put a picture of a RESTful API, I'd love to hear any ideas how you could do it. I haven't come up with one. So here's the titles of our doc. I looked at the WADL. The WADL file is even worse than looking at the API itself. But it's basically what you expect. Update, download, delete, get metadata, log in, all the usual sort of stuff. It's all done through a RESTful API. And it's all the sort of normal operations that you would expect from a file system type of thing.